in this video lecture, I will discuss the midpoint approximation, that is, how to use the midpoints to approximate the value of some definite integral. So all the problems of this type will have a definite integral that we have to find, and the end goal is to know how to use the midpoint approximation method. And we're going to be using this notation, so in which m refers to the method, so m means midpoint, and end refers to the number of, and I want to say rectangles, but it's better to say intervals here because it will not always be rectangles, and even it may not be, the number of intervals may not be a good name for it either, but n will refer to the number of something that we're going to be using as a measuring tool. And an example of a problem that we should be able to do is if we take this integral which was very similar to the one that we frequently see in statistics, and we can say something like, hey, compute this using M6, for example, right? So that's what we want to be able to do. Now, before we get to the midpoint approximation, let's briefly go over the other two basic ways to approximate a definite integral. I'm referring to left endpoint and right endpoint approximations. And as you would imagine, the notation that we're going to be using is ln for left endpoint and rn for the right endpoint, and L in the left endpoint refers to the method, again, R in the right endpoint notation refers to the right endpoint method, and N refers to exactly the same thing as we described earlier. It is going to be the number of intervals. In this particular case, it will be the number of rectangles that we're going to use to approximate the area. And let's, instead of me giving you a formula, let's try and develop the formula. So in this case, it's not, there are formulas that you may remember, but it's not about the formulas, it's about understanding the process. So let's use L4 to approximate this definite integral. So how do we interpret this question based on what we already know? L4 means we're going to be using the left endpoint approximation. 4 refers to the number of integrals, and everything else is pretty much given. So to make sense of this problem, we're going to draw this picture. And I'm going to draw some generic function, right? And we're going to be drawing it from the interval from 0 to 1. And I know what e to the x squared looks like, but I don't have to draw exactly that function to understand the process. So, but I'm still going to try it, right? So it looks something like this. And now, what does 4 represent? 4 represents the number of rectangles, so that's my n. When n equals 4, what is delta x equal to? According to the formula, it's b minus a over n. In our case, b is 1, a is 0, n is 4. So delta x is 0.25. So 0.25 refers to the width of each of the rectangles. And we're going to have 4 of them, and I'm going to draw exactly 4 such rectangles, and then using this delta x we can find this partition exactly. So it's going to be 0, 0.25, 0.5, 0.75, and 1. So we see how we have created 4 intervals. Now, what does it mean to use left endpoint in a left endpoint approximation? That means in each of these 4 intervals, we're going to pick a representative on the left end of each interval. And for each of those points, we're going to find the value of the function at that point. And we're going to construct the rectangles that are of the same height as the output at that point, but they extend horizontally all the way to the right. So let's find, well, the area of these 4 rectangles is what we are referring to as L4, right? So this is what we are looking for. We want to find what L4 is equal to. And now to find the area of each of this rectangle, here's what we're going to do. We're going to find the output of a function at each of these points. So this line segment is equal to f of 0. This line segment is f of 0.25. This line segment is equal to f 0.5, and this line segment is equal to f of 0.75. Now notice how the base of all of these rectangles is the same. It's delta x, which we found to be 0.25. And now we are ready to write the expression for L4. So L4 will be equal to the area of the first rectangle, which is f of 0 times delta x, plus the area of the second rectangle, which is height times base, the area of the third rectangle, and the area of the fourth rectangle. Notice how for the rightmost rectangle we don't use the rightmost point of the interval, we use one before that, 0.75. And what can we do here to ease the computations? We can factor out delta x completely. And now it's just a matter of figuring out the output of this function at these 4 points. So now we can either grab a calculator, or I'm going to use Desmos actually to make it easier. So let me pull that one up. I actually don't need to graph the function, but inevitably going to see the graph anyway. So let's just introduce this function. It's e to the negative x squared, and we define it on the interval from 0 to 1. This is what it looks like, kind of what I drew out, right? But again, we're not interested in the function itself. We're interested in the output of this function at certain points. So for that, I'm just going to create the table of inputs and outputs. And the first input I'm going to make is at 0, then at 0.25, at 0.5, and at 0.75. 75. And now, depending on your accuracy, you will round and we're just going to round to 4 decimals, which is pretty sufficient usually. And let's finish this problem, right? So we have at 0 the function is equal to 1, at 0.25 it's equal to 0.9394, at 0.5 it's 0.7788, and at 0.75 it is 0.5698. And now if we do all the math, everything inside of the parentheses is equal to 3.2880, and we're multiplying it by 0.25, and we're getting 0.8220, which is our L4. So the answer is, we approximated this definite integral to be approximately 0.822. Let's see what happens when we use the right endpoint approximation instead of left endpoint. So let's replace L with R, and let's recompute, or let's find what R4 is. And first, let's acknowledge that most of it will be exactly the same. We're still going to have 4 intervals, but right endpoint means we're going to be using right endpoint of an interval to build a rectangle. So we're going to use this as the height of the first rectangle, this as the height of the second rectangle, this as the height of the first rectangle, and this as the height of the last rectangle. And as you can see, a lot of the numbers will repeat. However, now instead of the leftmost point, we're going to be using the rightmost point, which is will produce f of 1. And the other values will be exactly the same. Now we're going to draw the rectangles, and I'll just draw them using orange. And so the area of the 4 rectangles shaded in orange is what R4 is. And to find R4, here's what's going to happen. We're going to compute the area of the first rectangle on the left, but now it's not of the height f of 0. It's actually going to be of the height f of 0.25. So what's going to happen is we're going to still use the 3 rectangles in the middle. However, on the right side, we're going to add the 4th rectangle, which is the area of which is f of 1 times delta x. So what's going to happen is, it's like we're just going to shift this whole thing. And we know in computations we're going to be using pretty much the same numbers, but the last quantity, f of 1, we still need to compute. So let's see what it is. F of 1 So f of 1 is 0.3679, and therefore the sum inside of the parentheses will be need a calculator for this one. So it is now 2.6559, and multiplying it by 1/4 gives us 0.6639, which will round to 40. So using the right endpoint approximation, we approximate this area to be 0.6640. And of course, both of these answers cannot be correct, so one of them is more accurate than the other one. But in order for us to see which one is more accurate, I guess we do need to find the actual integral. So what is the actual integral equal to? So let's just find the integral from 0 to 1 of f of x with respect to x, and the actual integral is equal to 0.07468. So that's the actual answer. And what do we notice here? We notice that the right end point is under by 0.08, and the left end point is actually above by about the same 0.08 or so. And but both of them are more or less of the same accuracy. Now let's make a few observations before we move on. We can easily observe that for decreasing functions, such as the one that we had, the actual integral is always going to be less than the left endpoint approximation and greater than the right endpoint approximation. And for increasing functions, the relation will switch. And the question is, can we do something about this? And well, the answer is, why, instead of us going from one extreme to another, why not just use, instead of the leftmost or the rightmost, why not just use the midpoint? And this is kind of the entire idea behind what we would call the midpoint approximation. And let's see how it works out. So let's take the same exact problem again. And this time we're going to be using M4 to approximate the same exact function. However, got to erase everything. I do want to bring the same line though, so let me try to fish it out of here. There you go. And this is our graph. And what does it mean to use the midpoint approximation? That means we're going to have 4 rectangles as before. We're going to have a partition made of 4 intervals. But now, instead of picking the left or the right endpoints, we're going to pick the midpoint. And we're going to create a triangle of the height equal to the value of the function at each of those midpoints. So an extra step that we're going to get here is we need to now figure out what the midpoints are. So that's actually pretty easy, because the midpoint is always going to be the left endpoint plus the right endpoint divided by 2. So that's the average of the 2 values. So the first midpoint will be 0.125. The next midpoint will be 0.375. The next midpoint will be 0.625, and the last midpoint will be 0.875. And now to approximate, that is to find M4, we're going to construct 4 rectangles. And the height of these 4 rectangles will be, the first one is the output of the function at 0.125. The second one will be the output of the function at 3.75. The third one will be the output of the function at 625. The last one will be the output of the function at 8.875. And therefore, to find M4, we're going to compute this 4 areas using the new heights. So the hardest part will be to actually figure out what those heights are. Meaning we would have to evaluate the functions at these 4 points, and as you do that, you may find it as something very tedious and time consuming. But remember, the other alternative will be nothing. We really don't have an alternative. This is the only way to compute this area, because this function doesn't have antiderivative. So again, let me just highlight this area, color coded this. So this is what we're finding, right? So we have 4 rectangles and we have 4 expressions to compute. So I'm of course going to use some technology, and I suggest everybody find their favorite technology and learn how to use it. It doesn't matter whether it's a TI-83 or Excel or anything else. You have to learn how to use it. I'm going to use Desmos real quick here. Remember, we're still dealing with the same function, so I'm just going to update this inputs. And I'm going to add all these numbers, 0.9845 plus 0. Actually, let's bring this over here first. And now adding those four numbers together, will give us the expression inside of the parentheses, and then multiplying it by 0.25 will give us the desired M4. So we got 29949, and finally multiplying it by so we get the answer of 0.7487. And notice how this was actually the right answer, which is a mystery to us because we don't know what the right answer is. However, if you now compare the three results that we got, one with L4, one with R4, and one with M4, we see that M4 gives us the more accurate one, and this is going to be the case for strictly increasing and strictly decreasing functions. And since every function can be broken down into intervals on some of which it increases and on the rest of them it decreases, then this can be true. Well, it is true for any other function. So M4 is a better estimate than L4 and R4 in general. For some specific functions it may not be the case, but in general it is a better estimate. Now, to summarize what we just learned, I guess we would have to write the formulas. So L4 was equal to f of x0 plus f of x1 plus f of x2 plus f of x3, and all that multiplied by delta x. R4 was f of x1 plus f of x2 plus f of x3 plus f of x4, all that multiplied by delta x. And M4 has a more complicated formula. It's f of the average of the first two plus f of the average of the next two plus f of the average of the next two, and finally plus f of the average of the last two, and all that multiply by delta x. So this is what we got for when n is equal to 4. Now, in general, you would expect this pattern to remain. So in general, what's going to happen? Well, we can just replace this with ... and this will be n minus 1. We can replace this with ... and this will be x sub n, and we can replace this with ... and this will be the average of the n minus 1 and the nth one. And we can improve this further, I guess, the way the formula looks, by using sigma notation. So instead of writing f of something ... we can just write f of xi. I goes from 0 to n minus 1 times delta x, and that's the left endpoint approximation. For the right endpoint approximation, as you may guess, it will be very similar. The only thing that changes is the boundaries from where to where we go in terms of I, the index, and last one, we can either write it like this, or we can also play with the index a little bit, and we can write it like this as well. So, as I said earlier, this is not about remembering the formula. This is about understanding the process and what exactly you're looking for. So if you understand that, then computing ln, rn, and mn is pretty straightforward. All right, so let's do this problem then. Now we're not going to have a function, we just are given a graph of a function. So let's compute m5. And to compute m5, we're going to take a look at the interval, and we're going to compute the delta x using this formula. So that means we're going to have 5 intervals of width 1, and starting at 1, here they are, right? So this is my x0, this is my x1, x2, x3, x4, and x5, and we're going to have 5 of them, 5 intervals. So this is my first interval, this is my second interval, this is my third, my fourth, and my fifth. And what does it mean to use the midpoint approximation? That means for each of these intervals, we're going to be picking a point right in the middle. So here's this point, here's the other point. And since we don't have a function given to us by a formula, we just have a graph. We don't actually need to know what those midpoints are, because what we care about is the output of the function at those points. So here we can see that the height of this bar is 7, the height of this bar is 8, the height of this bar is 6, the height of this bar is again 8, the height of this bar is 2. So when we construct these rectangles, those rectangles areas can be computed by multiplying their height by the width, and the width is equal to delta x. So m5 will be equal to f of the first middle point, I'll just write it like this, f of the second middle point, f of the third middle point, f of the fourth middle point, plus f of the fifth middle point, and all that multiplied by delta x. But again, we're not interested in this formula, we're interested in actual process. So this is just 7 plus 8 plus 6 plus 8 plus 2 multiplied by 1. So the answer is 21, 29, 31, whatever the units squared. So we approximate this area to be equal 31 units squared. So this is how we find m5, and you can imagine that you can similarly find m6, m7, and therefore mn for any n, which was the goal of this lecture.